Hello everybody, welcome to physical science today. So we're continuing our discussion on the kinetic theory. We've already had some talk about our little practice quiz there. Hopefully you learned something on that. So we talked about solids and liquids, and now today we also talked about thermal expansion. Okay, so what we said about thermal expansion was stated, volume increases when a substance temperature rises, for the most part. Now, there is one that doesn't change on a regular pattern, and that's water. So if you remember from earth science, water is most dense at 4 degrees Celsius, which is one of the miracles of life on Earth as we know it, because after 4 degrees, so at 3 degrees Celsius, it gets bigger, 2 degrees it gets bigger, 1 degree it gets bigger, and we know that at 0 degrees it gets really big, right? Because ice floats. If ice didn't float, and the reason why it floats is because it's less dense than the liquid water around it, so it kind of doesn't quite follow this thermal expansion idea as things heat up, they get bigger. I mean, it does for the most part, but there's an anomaly. And then the thing that's cool about that is, you know, if we had a big ocean or lake, and we had an ice form, and it was more dense than the liquid, where would the ice go? Down. So we get a chunk of ice here, and we get another chunk of ice here because it would form again, and another chunk of ice, and another chunk of ice. And solar radiation gets absorbed by liquid or anything that it interacts with and changes into heat, and heat is the random motion of particles, so the water gets warmer and thermally expands. But this solar radiation only goes so far. So I don't know, under like a certain depth, there's hardly any solar radiation that gets below that. Well, if the ice was at the bottom of the ocean, it would never heat up because it would never get that hot. Now there are, you know, currents and things too that can mix it up. But on lakes there isn't really currents, right? So every year a lake would freeze out. Well, what happens when a lake freezes out? Everything dies. Well, I should say everything, but the larger organisms die, the plants and animals die. And if that happened to our whole ocean, our lake would be completely different here on Earth. So water is one of those miracles of life as we know it, and it's different than most of the substances as far as thermal expansion. Okay, so gases then have an indefinite shape. So if you look down here in this box, what have you noticed? The gas is starting to fill that whole box, right? If the gas got bigger, what would happen? Or the box got bigger, what would happen with the gas?
The gas got bigger.
It would get bigger. If the box got smaller, the gas would get smaller, right? So usually what they say as far as gas shape is it takes the shape of its container. Okay, so you'll see that right here. Shape of its container. It has an indefinite shape by itself because it just keeps moving. And remember we talked last week about how fast it could be moving? Like gas particles could be hitting you this fast right now. That's a little fast for the nitrogen that's hitting you right now. I can show you the math with that in physics or AP physics later. Maybe in physics during this class we'll talk about the math. Well, 490 meters per second, or even 390 or 300 meters per second, that's fast. That's how fast you're getting hit with particles right now. Okay, so gas has a very low density. Okay, and if you take a look at that green box up there with the little antenna on top of it, that box has 6.02 times 10 to the 23rd particles in it. And when we spoke last time, I drew a box on the notes. I said, here's a box with 1 mole of particles in it. Remember that number? It's like a dozen. And I said, if I had a little pile of salt with 6.02 times 10 to the 23rd pieces in there, that's how much space a little pile of NaCl would take up. Well, if I would turn that into a gas, which almost impossible. I don't know, you can do anything when you get close to the sun and high energies, but a gas of a like particle would take up the space of a whole box. So 6.02 times 10 to the 23rd particles in that, or in the very tip of my finger, if it's a solid. So very, very, very low density, and because of that, we have high compressibility. So high compressibility would be like, show a little example here. If you go to NASA, Boyle's Law on Google, you will see this. And I'll show it to the class, and you can Google that at home. NASA, Boyle's Law. Okay, so those of you at home probably can't see what's happening on the screen, but at least you can look at the Google or the address bar, and you can see where to go, so you can join in on this visual aid. Okay, so it says right there that the attractive forces there are completely overcome by the disruptive forces. For your last bit of notes there.